All right. Hi, everyone, and thank you for joining us for Lunch and Learn webinar, Rethinking Net Zero, Designing for Energy Balance in Architecture, which is being sponsored by Wildan CETA. We are very excited today to have Vinod Sikar, who is a senior project manager for Wildan, join us. He has many great accomplishments and accreditations, PMP, CEM, WELL AP, LEED AP, BD plus C. Vinod is a senior project manager where he leads the implementation and operations of utility demand-side management programs across multiple states. With over 12 years of experience in energy consulting, he specializes in high-performance building design, decarbonization strategies, and energy efficiency program delivery. He works closely with utilities, design professionals, and building owners to achieve energy efficiency goals through HVAC system optimization, operational carbon analysis, and life cycle cost evaluations. His expertise also includes grid interactive buildings, renewable energy, integration, and helping clients navigate the transition to electrification and sustainability. Vinod currently serves as chair of the USGBC Iowa Board and as a board member of Anawim Housing, supporting affordable housing initiatives. He holds a Bachelor of Electrical and Electronics Engineering from Anna University in Tamil Nadu, India, and a Master of Science in Energy Systems from Northeastern University. So I'm very excited to introduce Vinod, and Vinod, take it away.
Thank you. Are you able to see my screen and everything's good?
Yeah, perfectly.
Yes, we are.
All right, so let's kick this thing off. Thanks for that warm introduction, and we'll get started. And as you heard, we are focusing on a net zero design or trying to reduce our energy use in the built environment and trying to maximize energy efficiency in the building and also investing in a lot of renewable energy into the grid. And as architects and building designers focus their attention to net zero design, there is a lot of interactions that are going on in the demand side of the equation, which buildings are one of the big ticket item. But there's also some dynamics to be considered at the grid level too. So this presentation is to kind of understand the overall impacts, not only just at the building scale, but what's happening at the grid scale and how buildings can be a solution to the problem of matching the supply to the demand for electricity as we move into a more sustainable future. So that's what the overall presentation is focused towards. So we'll be talking about the evolution of renewable energy sources at the grid level and try to understand what is net zero concept in your typical architectural design and how you play a role in reshaping the energy infrastructure and advancing some of the sustainability goals overall, and look at some strategies, not only at the grid scale, but also at the building level. So that's what we're going to be talking about. So I'll kick this off with talking about the evolving electric grid challenge, and then we'll dive into the components of a zero emission building and talk about non-building solutions and building solution, and then answer any questions you might have. So beginning with the evolving electric grid, just like rewind a few years back, we had an energy generation source far away. Either was a coal power plant or a natural gas power plant. It was generating energy, sending all those electrons through transmission distribution lines. And then you'll have a switch gear that steps down the voltage and delivers the power to your neighborhood network that's been used by the different buildings or different homes, etc. So the challenge is that every moment of every day, the amount of electricity that we were using had to be balanced by the amount of electricity generated. So that's a very delicate balance. The service providers have to anticipate what the demand for the next day is going to be and plan their resources accordingly so that they have enough power to supply the demand at any point of the day. So this has been done by what we call independent service or system operators, or regional transmission operators. They've got, these giant control rooms monitoring the voltage at various points, and they have to ramp up or ramp down to keep the fluctuations within control. And they might have some spinning reserves, typically that's typically natural gas or fossil fuel powered, that can come online in a moment's notice and can kind of balance out that uncertainty or unbalance in the systems. So if you have over generation, that'll affect your appliances, and there are elements in these circuit to kind of prevent overcurrent or over voltage. And if there's less than what the demand is calling for, you could have brownouts or blackouts. Then the cost of that would be pretty high. So just looking back to maybe 150 or 200 years ago, the grid was mostly fossil fuel based, and some hydro and nuclear plant kind of helped service the demand for electricity. And it was a one-way flow of generating power from one end and transmitting to the load centers. But now, as we go into a more renewable future, you're seeing a lot of interactions and microgrids and energy storage come into play. The best way I can explain this is now it feels like the grid has diabetes, and the solution, which is like insulin or like your metformin or whatever your uh, control devices are going to be essentially your buildings that can play a key vital role in minimizing that uncertainty in the grid. So here's an example of what the widespread solar impact is on the grid. So as we inject a lot of renewable energy into the grid, there is an uncertainty given that the sun is not shining at any given point of time. And if you have a cloudy day, or if the wind's not blowing, the load that the solar or wind energy sources was providing has to be met by an alternate source, either through natural gas or through any battery storage, for example. So here, when you see the graph to the left here, it represents the California's duck curve. That when you have so much generation from solar output, the overall demand or the loads during the middle of the day reduces drastically. And then it has a significant ramp up when the sun goes down. So we need to be thinking about energy storage devices that can shift the load from when the grid is less strained to when the evening peaks are occurring. So this is kind of affectionately called as the duck curve that's happening majority in the West Coast area. And especially, if you're thinking about electric vehicles and electrification, you can also kind of use those technologies for load shifting in the building. So when we look at the grid mix of California compared to the national levels, there's still a good amount of gas being used at the grid scale. But overall, when we move towards a future electric grid, we are expecting to see that fossil fuel trends go down, and the solar and wind investments will ramp up. So compared to like national average, you can see California grid mix is slightly different, and with the uncertainty in the renewable energy generations at different point of time, we need to balance some of those grid where the energy is coming from, and also understand the time value of your kilowatt hours at any given time. Here's a graph that shows that across the nation, if we electrify the building, the life cycle greenhouse gas savings are universally positive. When we took a study at switching some of the heat pump hot water and space heaters um, in the residential buildings. We noticed that the savings were almost positive across the country. The benefits, like with the electrification, is that if you just do nothing and just keep purchasing electricity from the grid, even your toaster oven is going to consume less carbon in the future as we inject more renewable energy into the grid mix. This is not the same impact when you look at the cost side. In some cities, the electric prices are more expensive than gas. So in those cases, when you try to electrify everything, the cost increase would be significantly higher in certain states. For example, you could see in Michigan, there's about a $700 premium. In the Massachusetts area, it's kind of a little bit neutral. But looking at some of the red areas are where you're expecting to see a higher utility cost, and this might be more felt by like even affordable housing projects or even low-income communities. So electrification, although it helps the environment in these cases or states, the electric rates are not set up appropriately to handle that switch. And given the current economics, this is a hurdle that we are dealing across some of these states. But the overall greenhouse gas emissions are all positive. That's what we're seeing from this study. So as things get more complicated on the regional transmission operators and the independent service operators, we'll discuss some of the major items that they could implement on the grid scale. So from a building standpoint, when we think about a zero emission building, we'll talk about the impacts that buildings have as part of this problem. So buildings almost consume 40% of your overall energy use across the nation. And if you break that down, about 30% of that is from embodied carbon. This is associated with the building materials and the initial energy that goes into mining and bringing all those building elements together. But almost 70% of the carbon emissions from the building sector comes from the operation side. So this is where the majority focus is to reduce the ongoing operational carbon emissions for the buildings by investing in energy efficiency and also renewable energy technology at the site level. And another item that we also have to keep in mind is the site to source ratio or the site to source conversion. For every unit of electricity that's generated, or the other way around, for every unit of electricity consumed at the site, there are almost 3 units of electricity produced at the generation capacity if you're relying on the grid electricity. So there's also this site to source conversion factor that needs to be considered. So there's a higher impact at the source level when you're saving even just 1 kilowatt hour at the building level. So there is a call for zero emission building definition, and there was a request for inputs from different architects and engineers, and then there was a definition that was released. And why this definition is important is that we're intending to provide guidance to help support the building sector move towards zero emissions. And part of this California Energy Design Assistance Program is also to work towards a decarbonization plan and move away from fossil fuels and focus on all electric buildings and decarbonization overall. So the national definition of a zero emission building is on 3 of these criteria. At minimum, the building has to achieve zero operational emissions from energy use that's going on in the building. It has to be energy efficient at the first level. And then once you're maximizing energy efficiency in the building, the additional energy that is remaining in the building must come from free carbon neutral sources. And the third one is you have to be powered completely by clean energy. So these are the three critical factors that one should be considering while designing towards net zero. Is try to maximize on energy efficiency first. This is the cheapest resource in terms of demand side management compared to the currently existing technology that's available in the market. When we look about embodied carbon, as we talked about, which contributes to about 30% of the emissions, this refers to, like bringing those raw materials, mining those materials and manufacturing them and bringing that to the site, and also disposing once the building is used. And there's a cradle to grave approach of thinking about these embodied carbon. And there are some additional tools that can help you look at the embodied carbon at a closer level, since building, as they get more efficient, then the ratio of that's 30-70 might switch to heavily on the embodied carbon if you're dealing with net zero building at an operational level. So let's talk about a few of the non-building solutions, and then talk about the building solutions. So when we talk about the non-building solutions, this is going to be coming from the transmission distribution side, the utility provider, or the regional transmission operator. So on the grid side, the RTOs and ISOs, they are thinking about distribution planning. These planning projects take about at least 5 to 6 years to come up with a plan and have those approvals and then turn into a construction project. So the simple idea behind this is that the sun is always shining somewhere and the wind is blowing somewhere. So why don't we just interconnect these different parts of the country so that we have a more stable source or generation capacity? And as I mentioned before, these planning projects take a long period of time. And in terms of implementing these distribution projects take at least 10 years or long to get those permitted and built. So that's one challenge of kind of completely relying on distribution networks to come into play. Another option could be peaking plants. So when there's a dip in the solar output from a solar farm, or when there's a huge drop in wind generation in the middle of the night, you can't rely on fossil fuel generation for operating at a smoother capacity. The issue with this technology is that you're going to be having those natural gas power plants on call, in the sense they are spinning reserves and they're ready to go at a moment's notice. So they have to be running, and then they will be consuming energy just to be idling. What we found in one of the study from one of our subsidiaries is the lowest cost to build and operate an electric system, the ratio or the sweet spot is 80% renewable energy with 20% of natural gas to make up for that variability. So I'm not saying we have to completely eliminate fossil fuel energy in the grid, but these are going to be critical in terms of in those unreliable times where the sun is not shining or when the wind is not blowing. Utility scale storage projects are also coming into play when there's plenty of solar capacity available in the middle of the day. You can store that and discharge it at night. And then there are also some additional technologies like flow batteries, or grid capacity level that's in the range of 5 to 10 megawatt capacity that can be implemented in addition with the renewable energy projects that can provide some stability. And there's also a few classification on those technologies, whether it's short-term storage or long-term storage. And apart from batteries, there's also some other pumped hydro technologies or thermal energy storage technologies that are also being considered at the grid scale to be a little bit more cost effective. The issue with that relying on batteries is that, if we focus more on electrification and if everybody moves to an all electric building, with the associated load growth, there's not enough lithium left in the earth to kind of manage those uncertainty. So instead of just relying on battery technology, the grid operators are considering multiple different technologies as part of their resource mix instead of just relying on batteries. And they've been proving to be a little bit more cost effective overall, just compared to battery technology. And the last approach is just overproducing. So just having additional capacity when you have a lot of investments in solar and wind going. If you are just, instead of meeting base load, just designing for the peak load, and then kind of curtailing the production during the peak hours could also be another option. Or with using that additional energy for hydrolysis and providing green hydrogen is also another option that the operators are considering. So all of these four different options that we talked about are going to have capital cost associated with that, and are going to be eventually going to be passed on to the ratepayers. So that's the disadvantage of these large scale projects that take a lot of time and effort in terms of planning. The good news is that what we're seeing as the planning projects for the next few years, about 90% of the projects are either solar or wind or some kind of combination of combined cycle plants that are using low hydrogen or low carbon fuels like bio, um, diesel, or a cleaner energy source, for example. So the big takeaway here is that the grid responsive buildings will take less infrastructure and cost. So here are some examples of California's grid scale battery projects. So here, we talked about that duck curve where you have a lot of peak generation going on during the middle of the day, and we are shifting the energy from those low demand to the high demand areas. And then California is also requiring battery storage for some of the newer projects that are coming online. So what the battery storage kind of enables is it provides that resiliency or reliability, and also the ability to switch your loads from one part of the day to the other. The round trip efficiency is about 95% for battery storage, meaning if you put in 1 unit of energy for storage, you can get about 95% of that back, with assuming there's some inverter losses on the way. So here's an example of a 750 megawatt storage capacity connected to the California power grid. It's it's the world's largest battery storage facility, and that was kind of in the California area that was began to operating a couple of years ago. Let's talk about the building solutions here next. So as we shift from the net zero energy to net zero carbon, we have to be thinking about not only uh, how much we are using in terms of energy, but also when we are using that energy a little bit closer. So we are relying heavily on on-site renewable energy generation for some of the offsetting some of the remaining energy once we've maximized on energy efficiency investment. But we can't just completely rely on that. So that's why we are thinking about different approaches to this problem. So the net zero carbon kind of combines those three definitions that we talked about is maximizing efficiency first. So reducing that, the curve overall, and then implementing renewable sources, and then using low carbon materials at the building level to reduce embodied carbon. So when the reason why we keep saying energy efficiency first is if we don't focus on efficiency first, then it is like adding clean water into a bucket that's already filled with holes. So you end up producing a lot of energy, and that's being utilized in an inefficient manner. So the slogan or the mantra that you want to keep in your mind is reduce before you produce. So focusing on efficiency not only helps your bottom line, but it minimizes your overall cost and grid infrastructure. It improves occupant comfort and health, not only at the building occupant level, but also at a community level. And but we can only go a little bit far with the efficiency. So once you get to a 40 to 50% range on the efficiency scale, what happens is that you will see some diminishing returns on your investments. So that's where we need to know when to stop investing further into efficiency and switch to renewable energy sources. So once you get to that, 40 to 50% range, and compared to your base design, at that point, a little bit investments kind of doesn't go farther in terms of returns. So you'll probably be seeing a big spike in capital cost with little margin in terms of gains. So uh, the the sweet spot is around the 50 to 60% range when we're looking at the switch over to renewable energy investments. So here's a few examples that will be talking about grid interactive efficient buildings or GEBs. So what does buildings have in terms of capability? It is smart, it is connected to the grid, and it kind of continuously monitors the grid state and how the carbon signals are changing based on hour by hour or even minute by minute, and kind of respond to some of those signals and either minimize the load or shift the load at a certain time of the day to kind of optimize the overall carbon intensity of the building. So the grid interactive efficient building is led by the Building Technology Office, and it is kind of looking at the fundamental research and development of these different technologies and see how we can bring this to um, like the market in both residential and commercial building. At homes, you might have seen these smart thermostats that also play a key role in shifting or minimizing your utility bills. I do have a Ecobee at home that kind of helps manage some of the utility bills on my end, knowing that if it's a hot day, it'll ask me like, can I set back the temperature a few degrees? And that there's also some behavioral changes that go with it. So the more the occupants are also educated about these technologies in the building, that helps kind of realize the savings a little bit more. So there's some educational competence as we bring these additional technologies into the building as well. So here's an example of a grid interactive building that was completed a few years back that had PV and battery storage. So it's more of a microgrid, and we can see that these homes are about 35% more efficient than the average home in Alabama. And the microgrid is owned and operated by a local company, a utility company. The system integrated in these communities are pushing the envelope and testing how new technologies work together. Although, the ideal need for natural gas generation will go away, um, and another example that comes to mind was one of the microgrid community in the Florida area that was impacted by some of the storms last year, and where the overall community was in survival mode. That microgrid community had some on-site generation and battery backup and was able to withstand some of those climate impacts as they were kind of going through the hurricane season. So apart from the carbon savings, there's also this resiliency aspect to be considered when we are thinking about these additional technologies, especially when they're a little bit cost prohibitive or doesn't have the favorable payback periods for your project. Here's an example of the demand side management, or the power of demand response programs. So early in September 2022, there was a big strain on the grid, and the demand for the electric grid was an all-time high. So the California governor sent out a text message to all of the residents saying, we are experiencing this demand response event, and asking the residents to conserve energy. At least it's not charging your mobile phone, or reducing the load in the building. And the response was pretty tremendous. They were able to drop about 3,000 megawatts in a few minutes just from that one text message. But the more robust automated demand response program would have gotten the same effect, but with less disruptions. And I'm sure you don't want your governor texting you every single day to stop using energy, right? So that's why we need to be thinking about this ahead of time to avoid some of these situations. So when it comes to demand response, we're not using less energy, but we're just shifting the energy from one point of day to the other. So there are a few methodologies that you could use. Is shaping the curves, which is with a lot of advanced notice, or with technologies like heat pump, hot water heater that are programmed to change the load or profile on a daily basis. The other one is like shifting energy. So it's moving from high demand with surplus energy to a low demand time, just like ice storage, for example. So you could store ice or generate ice during night times where the electric rates are low, and then use them in the evening hours when the rates are high. So that's a different part of thermal storage, that you're shifting load from one part of the day to the other. The third option is shedding the load completely. This is curtailing in terms of setting back your thermostat set points a few degrees, or turning off the lights, or dimming the lights at a level that you hardly notice. And with a lot of LEDs technologies in the market these days, these can be even automated. And the fourth option is shimming. These are very micro level automation changes, whether it's starting your compressors or starting your high load equipment. Even if you change those at a microsecond level, that could have some huge peak demand reductions when you kind of aggregate those all together. The Grid optimal, the New Buildings Institute came up with the Grid Optimal Building Initiative. This gives the building designers a few metrics that they could follow or score for their design for the building based on different categories. So this has been widely used. Even LEED has a point for this grid optimal metric. So what it does is uses the National Renewable Energy Labs Cambium database, which helps us look at some carbon emissions into the future with different varying scenarios or uh, what if uh, the the policies change or if the natural gas prices fluctuate. There are some few different scenarios that helps us visualize how the grid mix might change into the future, and using that information to then score your building's energy usage at different times. So this particular tool is a good reference point when you're considering some of these peak shifting or on-site generation strategies for your building. The diving into the different metrics, there are about 8 or so different metrics that you could target. The first one on the bottom is just your efficiency, how much you're better than a typical baseline. So it's kind of the first step, I would say. And then the next one is grid carbon alignment. So this is trying to match your building's usage when the grid is less strained and cleaner than when it's more strained and dirtier. And then on-site renewable utilization efficiency, whether you have enough capacity in the building to use up all the energy that you're generating on the site, or you're overproducing and then exporting it to the grid, especially when the grid also has so much energy at that point of time, and they really don't want any excess generation at that point. So it's almost like you just finished having a Thanksgiving dinner, and your neighbor brings over more food to you. So it's kind of that analogy is that when you're able to produce more energy is also when the grid also has those similar technologies added to the building. So instead of exporting it back to the grid, this helps us kind of see whether you're able to effectively use the entire generation capacity at the building level to meet your loads in the building. And then the typical metric that we often see is the grid peak contribution, whether your building is peaking at an hour, maybe in the evening when the grid is trained, or whether it's peaking at an off peak at nighttime, for example. And as we go into the resiliency and the uncertainty part of the equation, that's where your battery storage or other thermal energy storage comes into play. So here we can also look at short-term flexibility, which is just for 1 to 4 hours in terms of battery backup, for example. If you're able to shed the loads or completely offload your building's energy use into like a backup system. The long-term demand flexibility is going to be rated for at least 4 hours of time. And then dispatchable flexibility, it is the time where the event calls by the regional transmission operator or utility company to asking the building operator to switch their loads to a backup source. So it could be calling ahead, and they can sign up for these events and kind of get some additional incentives through the utility program too. So there's the building ability to kind of shed the load at a moment's notice is dispatchable flexibility, similar to like the demand response programs. And then resiliency is you can completely island from the grid for about 24 hours. And this helps more for like hospitals or community centers where they could provide some additional services to the community at a critical times like natural disasters or wildfires, for example. So we talked about the shifting and shaping, but the issue with the electrification process is that when we electrify a building, we have to think about efficiency first again. Here's a comparison of the baseline and the proposed peak demand on the summer and the peak demand for the winter months. So this is for a sample 100,000 square foot office building with a VRF system as the design. So when we are electrifying these buildings with some all electric systems, the shift in the peak is going to come in the winter months rather than the summer months. And if we don't apply efficiency first, then the delta going from the baseline to the proposed, you could see, if I could bring my pointer up here, the efficiency scenario is in the dark blue line, and the light blue line is the baseline scenario without efficiency applied. So you can see the difference between without efficiency and with efficiency is not that drastic during summer months. But if you electrify without considering efficiency into the picture, your spike in the peak demand is going to be significantly larger. And it's going to take the utility companies a lot of investments to control or minimize that peak demand. And with all electrification happening, we are going to be looking at utilities moving from a summer peaking issue to a winter peaking. So that's also something that we need to be thinking about long term when we electrify all of the building loads. Another issue about the solar generation for an office building is when you have excess capacity, for example, especially during holidays, you can see for a July 4 weekend, about 300 kW of this building's energy load is being sent back to the grid on Tuesday afternoon when the building shut down. And then the next day, the building comes online and they're using a lot of energy and they're asking for 300 kW demand from the grid. So there's at least a 500 kW difference in the swing just between holidays. So that's putting a lot of stress on the utility. So this is where kind of on-site storage also makes sense. And going back to that, the diabetes example is trying to control that swings and trying to balance those loads so that the utility provider is not coming up with the additional generation capacity to meet your load. And when they have to do that, they typically go with some of the fossil fuel-based generation sources, which leads to more carbon. So the buildings, instead of being part of the solution, would just be part of the problem at that point of time. So that's when it's kind of critical to think about on-site generation coupled with battery storage as kind of the sweet spot of the combination. Here's another example of demand flexibility during those different hours, or the short term versus the long term dispatch that we talked about. So, for not all utilities offer the demand response program, but we are hoping to see load flexibility and the ability of the building to kind of respond to carbon signals is also another feature that we could bring if we have this demand flexibility in the building. And it's not just all like additional batteries or thermal energy storage. When we start from the basics, we also need to be thinking about insulating the building and minimizing infiltration into the building. So here are some other building strategies you could consider. So typically solar panels are faced towards the south to maximize generation. But if you were to face to the west direction, that can help you provide late afternoon generation. So it kind of switches the curve a little bit. You can think about including automatic demand response and even HVAC lighting and surface water heating systems if you're not able to invest in battery storage. What this does is, it can pre-cool the building or preheat the building a few hours or a few minutes in ahead of the demand response event. Also, you could preheat some of your hot water systems to account for that usage later and kind of shift the load a few minutes. And then use renewable energy whenever it's available in abundance, especially if you have like a pool in the building. You can kind of store that energy into that thermal mass a little bit more, uh, or even pre-cool the apartments before you get home so that you don't get hit with that evening spike in increased utility rates. The the image to the right is an example of the Icebox challenge that was done a few years ago. That, if you recall, they basically put a ton of ice in a normal building versus a passive house building, and what they found is that in LA, the the summer heat of maybe 90 degrees, they the typical core level building versus the passive house building was able to withstand the temperature to about 70 degrees compared to the 90 degrees that was like the typical core baseline building. So, increasing your insulation levels in the building would also help you kind of maintain those set points, and also allow you to kind of pre-cool or preheat the building and shift the load better and minimize the winter peak demand in terms of going towards more efficient system, and also you could avoid nighttime setbacks that would increase the demand during the startup period early in the mornings too. And then the shells can also play into the equation in terms of designing more better insulated buildings and reducing your filtrations that can help you with maintaining set points in the building. So just wrapping up what we talked about, the good design for net zero is not only just an efficiency or not only just adding solar panels to the building. It is a combination of variety of technologies and trying to understand when you're using energy and how you're using those energies and how that ties with the grid conditions too. So the buildings become part of the solution and not just blindly adding up your energy and making the solar panels produce that equivalent amount of energy to get to net zero. So we don't want to be net zero just to get to net zero, but we need to also think about the grid impacts that the buildings have and how it can respond to the grid signals and the pricing signals as well. And as we mentioned several times during the presentation, we need to focus on efficiency first and also consider grid interactions. And we need to build a building that can reduce the load during peak conditions and allow for demand flexibility. And energy modeling can help you find that right technologies and the balance in terms of different energy mix and also different strategies within your building too. So that takes us to the end of the presentation. I believe we've got about 5 minutes left. Just wanted to see if anybody has any burning questions. And then I'll leave my contact up on the screen too, if you want to reach out later.
Vinod, there was a question in the chat for you. Let me pull it up. Dennis asked, what type of batteries at Moss Landing?
That's a good question. Let me check. I don't remember at the top of my head.
Yeah, I'm looking it up online now. So, but thanks. It was a, a good reference. It looks like some interesting articles about the power station. Thank you.
Yeah, thanks.
Well, apart from lithium batteries, what other kind of storage is being explored?
Apart from lithium ion, there's also this hydrogen-based technology where you could generate clean hydrogen through the process of electrolysis, and then use that hydrogen as a fuel source to produce energy in the building or later at time. There's also some flow batteries that kind of use some unique chemistry to have that reversible cycle. So you kind of use that electricity to break down the energy between the anode and cathode, or basically recharge the batteries and then use those later. There's, with hydroelectric providers, there's also pumped hydro. There's compressed air technologies. And there's also these phase change materials that can switch over from solid state to gaseous state, and can store that energy through the latent heat. Also similar to like ice storage, there's a significant amount of energy that's being stored when you have phase changes. So there's a lot of phase change materials that are also part of like insulation systems. And so between like thermal storage and even I saw like a unique storage. I don't know if it's commercial yet, but it's just lifting these cinder blocks at a higher height. So storing it as potential energy and then bringing it back when you need electricity, and bringing those cinder blocks down to generate electricity. So there's some reversible process that are still being studied and evaluated. But a lot of utilities are investing in some of these studies and trying to calculate what's kind of the best optimal approach, and not put all their eggs in one basket, but also invest in these different types of energy storage devices or technologies.
Well, it seems like this has always been the problem. I mean, the sun, the wind, the water, it's always been with us that we've been able to use and harness this. It's the storage that is part of the, well, seems like a major problem. And as you pointed out, the sun is always shining somewhere.
Yeah.
So it's startling that we haven't progressed much beyond the 70s, really, just improving batteries. But I'm startled that we almost seem to be at the beginning of the process. Where are those physicists?
Yeah, and there's also these policies and the infrastructure constraints. Texas is still its own, it's under its own transmission, and you saw the downfall when they had some unexpected winter storms and they completely had a blackout for the entire state. And some of the residents had like a $20,000 utility bill because they had some time of use pricing. So these are some like disadvantages of not having systems interconnected across different states, and there's still some policy aspects that needs navigated.
Well, Texas actually, even though it's as we know, a big oil producing state, it's been rather progressive with wind. So it is odd that whole blackout happened for them.
Yeah, it was during a winter storm, so I don't know if it was again due to the imbalance of the supply and demand. If those are not well regulated or managed, those lead to blackout, and then starting those systems take quite a bit of time and effort. And the other big challenge we are seeing with the increased number of data centers and increased AI, there's a lot of load growth across the country. The good part is that they have some good base load instead of going up and down at certain times. So those projects kind of think about these different demand response and demand management strategies from the get-go.
Are the Bitcoin mining data things, do they take up as much energy space as the data centers, or even more because it's a constant movement?
Those definitely take up significant amount of energy for mining, and it's almost equivalent to like having a grow house, for example. It's that energy intense, and those type of operations can shed their load at a moment's notice. So they have some demand flexibility just from the operation perspective, but they are pretty intense in terms of energy use.
Thank you.
Yeah.
Any more questions, anybody?
So do you see any like really big shifts in the near future in all of this? Is there something on the horizon that we can be happy about?
There's a lot of investment going on in the fusion energy, so we'll see how that spans out. There's a lot of investment in solar and renewable energy generation. The cost of those have been coming down slowly, and you're seeing a lot of even at the building scale, or if the building installation doesn't make sense, there's a lot of effort from the communities to kind of pull up resources and have like a community solar farm. So that's kind of helping us kind of resolve at the microgrid level. The kind of the analogy I have in my mind is like growing your own like community garden, for example, or growing veggies in your backyard. Instead of going to the grocery store every time you need something. So it's kind of that how you can break down these different pieces at the building level and have some resources or capacity if the grid is overall strained.
All right, everybody. Well, thank you so much. This was a fantastic presentation. You did such a great job. Thank you also to your colleague, Claire Cole, who couldn't be with us today, who was great in helping us organize all of this. I do want to plug just a few things for everybody. We have our Design for Dignity conference coming up in 2 days. Or it's going to, sorry, not in 2 days, but it'll be 2 separate days, Friday, June 13th and June 20th. So we would love to see all of you come out and support that. It's a really great conference that focuses on housing inclusivity, social inequities, and then of course the recent disasters and what the county and state plan to do moving forward. So it'll be really fantastic, and it's from 7:30 to 12:30 both days. I did put the link in the chat for everybody, and then please check out any more upcoming events. And thank you again to Wildan and CETA for sponsoring this. We appreciate all of you spending time with us today.
Yeah, thanks everyone. Have a good day.
Bye, everybody.
Very good. Thanks.